And welcome back everyone to our OpenFoam discussion. In the last video we're trying to validate our results, and apparently there was this mismatch that you see right here on the screen, and we are wondering why is this mismatch happening. So there are a number of things that we want to investigate, of course. One is that the mesh is too coarse, right? The mesh is too coarse, meaning to say that if you look at the mesh of the hot sphere in oil, you can see the mesh size is pretty big, and that's why it calculates relatively fast, like 5 minutes you can calculate a 2-minute case kind of a thing. So that's one possible reason why, but that probably won't account for like a difference of 2 to 3 times kind of things. Like the Nusselt number here is like 10, the Nusselt number here is like 30, so there probably might be something else at play. Second possible reason, the thing is that the correlation was developed for steady state, but the experiment was in a transient thing. But then again, if you go and search online, okay, I just googled, what did I google? And yeah, convection correlation for transient cooling spheres. I think one of the first results is this Transient Labs sample report from Washington.edu. If you take a look here, they use the same correlation with the same Rayleigh kind of Nusselt number correlation. You can see here for spheres. However, they're also doing a transient kind of experiment where they have some gold plated sphere or something like that. So they insert in hot water bath and then let it cool in air and they remove the plastic sheath and all that kind of stuff. So this is something, this is what available online, one of them available online, and this correlation seems to work for transient case. So what else could be the problem? Well, one of the things notice here is that we have, let's say, see the beta value. So this is the beta value of ideal gas. So this is the volumetric thermal expansion coefficient, and for an ideal gas, the beta is 1 over TF, where TF is the film temperature. So that should immediately spark some alarm bells. Okay, they did not use the bulk fluid temperature, which is T infinity, but instead the film temperature T infinity plus Ts over 2. So yeah, probably what we were doing is to use all the bulk fluid temperature. So instead, we can try using a film temperature instead. The film temperature will be a lot more robust, probably. The way we should use that to get the value of beta and of course the value of nu and alpha, or the Reynolds and Grashof number and the Prandtl number. They should be based on the film temperature rather than the bulk fluid temperature. So probably we want to do that before making changes to the mesh to make it a better shape. Okay, so again we will need to do some calculations on that. So that's what this video is going to do. We're going to look at the first possibility, and of course this one was actually advised to me by a friend also, like a good mate. He also suggested the same thing. I will not put his name here for privacy purposes. So okay, next thing, first thing first, let's clone this, move a copy, okay, create copy and move there, heat flux data. Okay, so I'll name this thing called variable property calculation. Temp varying calcs. Okay, so this means things are supposed to change with temperature, right? So first thing first, we need to I want to delete a lot of redundant data. Okay, so first thing first, I want to get rid of everything to the left here. Okay, Everything to the left I don't really need because that's already available in the other ones. What I want is a Prandtl and a Grashof number. Okay, and of course all of this relevant things as well. So what I'll do, is okay, I have a Nusselt number here, I have the heat transfer coefficient here, and the surface temperature here. So I do not, none of it is it's reliant on the data on the left, so I'll just delete it. Okay, so I'll save. Okay, so Nusselt number is here, heat transfer coefficient is here, and K, which is the thermal conductivity of the fluid, should change with temperature, and it should also be based on the temperature as well. So what I'll do is simply insert a few more columns, and let's have a temperature dependent K. So K as a function of T. So what's K as a function of T? You take a look here. I'll just copy and paste the correlation. Okay, so this was a correlation which is 0.00016 times 0.1856. Okay, there's a linear dependency on temperature. So I'll copy this and I'll paste it here. And instead of 300, I will just use okay, the temperature. Okay, I think I should copy and paste this over. And let's do T film temperature. Okay, and that will be equals to Ts plus T bulk over 2. Okay, so the bulk fluid temperature is 300 Kelvin. Okay, and T film will be average. So this is an ensemble average. So I lock this and I'll average it with this, and that will be the fluid temperature, the film temperature. Okay, so that should be it. So this will be the K thermal conductivity of the fluid should be based on the film temperature. So let's do that. K is equals to this correlation, and we'll use the film temperature. Okay, and there we go. So it's about 0.12 to 0.13. Okay, starts at a lower thermal conductivity and it goes to higher as the temperature drops. Alright, so that's the trend that you see here. So Nusselt number CFD as a function of T film. Alright, that will be simply H, heat transfer coefficient, times D, diameter, lock this down, divide by K. And the Nusselt number actually increases to about 18. So there's a steady increase in Nusselt number, except for the last value, it looks really pretty similar, okay? About 10. So that's the Nusselt number. So this I can just delete. Now, next thing I want to look at is the dynamic viscosity as a function of T film. T film, because the next thing I want to calculate is the Prandtl number. Okay, next thing is the Prandtl number, so I'll start with dynamic viscosity first. This one is just a value. I do not want that. Yeah, this is just a value. I can just delete it. We'll have dynamic viscosity first. And what is the correlation? It is over here. So I'll just copy and maybe I just copy this over. Okay, I'll just copy and paste this over, and I can slowly, have this correlation here. So again, it looks very long, so I'll just zoom in and copy and paste over. Okay, so 1 is equals to this number times this number times the t to the 6, t film to the 6. Okay, that's the first one. Second one is maybe I'll just do this. It's a lot easier. I'll just copy the whole thing. Wherever I see an x, I'll just put a C6 to the 5th. Yeah.
The thermocouple specific features here. Aren't they worth having for our thermocouples instead of having
To the 5th. Oh, it's much more efficient.
What you currently use? You currently use a thermocouple specific
Times C6 to the 4th.
I think that
Times C6 to the 3rd. So I'm looking at the top bar here. Times C6 to the 2nd. Okay, this one will be times C6. Okay.
I don't know. I don't think
Forgot that.
I don't think that this provides any additional.
So the dynamic viscosity at about 400 should be less than 0.001. It is. And that is right. Okay. So that's how to do the dynamic viscosity. And then I'll just bring it all the way down here. Okay. So dynamic viscosity changes by quite a fair bit. So the Prandtl number will definitely change as well. And once I'm done, I can just delete this. Next thing, Prandtl number. We'll need for Prandtl number we will need CP data. So constant pressure heat capacity, same deal.
I'm just curious with the
so I will take a look at the CP. Where's the CP? CP of the oil should be here. This one. I'll do the same thing. Alright. So I'm going to equal.
Plug your thermocouple straight into here.
I'll copy and paste it in.
Buy a compatible thermocouple chassis, and then this plugs in. See it.
Okay.
They have the,
so again, x to the 4th.
frame, and it has
I put times C6 to the 4th because that's where the temperature is. Times C6 to the 3rd. Times C6 to the squared. And times C6. Press enter, and there we have our CP value. So the Prandtl number will change with temperature. Okay, so now we have a temperature varying Prandtl number as a result of the T film. Okay, so what is it? Mu times CP divided by K. So instead of 30 something, 40 something, it starts at like a value of about 11. So we can do that. Start from 11 and go all the way up to about 39. If we look at our Prandtl number last time, it was about 43. So there is some difference there. We should be pretty mindful of. Okay, so Prandtl number as a result, function of T film, it will be different. Now, next thing is we need density data. Density. So what's our density function? Density function we can take a look at this.
I think, what if we do this? Let me write down,
Okay,
just so, I know
where's our
I've wrote
density?
one, but let me write down my requirements. Alright, and then
Yeah, this is the correct graph.
call NI.
Okay, chop chop.
Get advice from them on what might be the best combination of devices.
Yeah. Oh man, look, you can get 32 outputs.
Mm,
Output voltage range.
C6 to the 3,
Sorry.
C6
Yes.
squared,
Yes, I could. I think I'm starting to
C6.
understand stuff
Okay,
well enough.
that will be good.
So let's go back to here. So for a PC,
Okay, so that's the density change over temperature of the film. And
If we think
I will have one column here for d rho dt and one more for beta.
thermocouple blocks. This is assuming no
So let's take a look at what is
I can still do it. See
the appropriate
actually, this is
coefficient.
whether we decide to do a pixie or all of
Yeah, let's
all
take
of
a look at
these
the proper coefficients.
now.
I'll just calculate all of this
Just
over.
making sure that our computer
I mean,
that
no,
we get
I'll look at this one.
has options to
So
like if
should
if
look
we
at this
can
one.
plug in more of the PXI. No, PCI.
So it seems like if we get that
Okay,
control adapter or whatever.
so this is the one here.
Then you
I
would
just
only
highlight it in gray.
one connection to
To the computer.
So I can delete it
and
later.
that PCI board
First thing first
really
is
that adapter.
5.2 times 10 to the minus 6 squared. So
That seems
this one is a t squared thing.
possible. That sounds
6
right.
squared.
But in either way, like for me,
This one is with respect to t plus
I want
this
to
times
the
c6,
Wi-Fi, I can just go ahead and do it.
then plus a constant, which is this.
I was like, but I
Minus
know
this. Okay, sure.
now
So now we have our
that
d rho dt, change of density with respect to temperature.
that if I
Okay, so this one I can delete it off.
I need at least an analog input card and an
Okay.
analog output card.
And now we can calculate a beta value, which is 1 divided by rho times this d rho dt. That will be our beta value.
Man,
And it stays pretty constant. I mean, pretty much in the same
my
region,
analog
which is
input
fine.
card-
Right. Next thing is the Grashof number.
my analog input card
Okay.
is going to have. I can put.
So Grashof
if
number will
depending
be,
on the type, if I
first thing
I get
first,
one
I'll
that's
need
just
to,
for thermocouples, then
I'll
I'll
put
need to
this
do a
over here.
thermocouple one and then another one for whatever other things that I want.
Okay, so it's 9.81
My
times,
general
okay, that's G into, I need to have a beta
one. Or
over here.
and then I would need two inputs and an
Then I'll need the T surface minus, was it T film? Yeah, but T surface first.
So
Let's do T surface.
Wi-Fi.
Surface temperature here, A6. Okay, next thing is the diameter cube, which is that.
There is
And
no
then you have density.
for Wi-Fi, right?
Density is
There's no multifunction
here.
for Wi-Fi.
There's no multi, so there's no
And we
input
will be
output.
So you
dividing
need
that by
analog
the
and
viscosity
analog
squared.
Yeah.
Dynamic viscosity is here. I'll do it like so.
shared pixel.
But see,
Looks like we have a negative number.
Yeah, and
for
so
some
with-
reason.
With this one, put Wi-Fi next, like, I mean, there's three. Those are three.
Okay, so
Oh, it's,
9.81
Wi-Fi
times
three.
M6.
Yeah, these are 3 modules.
And then I would need 3 chassis.
Oh, beta,
as
yeah.
well.
Oh,
I think
no.
beta should be
Wi-Fi chassis.
positive. So that's the Grasshopf number.
We can do a cost analysis first.
And then I'll have the Grasshopf number calculated for everyone. And of course, I can move it into a scientific format, so that you can see what's the thing like. So this is 10 to the minus 10 to the 7, which is again lower than 3 times 10 to the 8. So laminar properties are perfectly fine. We can see Grasshopf number actually changes by a few orders of magnitude, rather than before where it was a pretty linear thing.
And you're not worried about
Yeah, a few orders of magnitude. Hey, it's not
that now
okay.
not having
Both times it changes. Okay, so maybe now it changes more. I'm not that sure. Okay, but okay, I can just do a quick check here.
isolation. I think the key is
Here,
what kind of
3 times 10 to the 6,
This says channel to channel
all the way
isolation.
down.
I'm curious what
Scientific.
the other one, I think the other one says something like bank isolation.
Yeah,
Too bad.
doesn't change as much. Anyway, let's look at the Rayleigh number.
Only
It's
2.
too small.
Alright.
Okay,
So
Rayleigh
assuming
number is just a product of Grasshopf and Prento.
so
Grasshopf times Prento. So it's 8 times 10 to the 8, which probably there will be some turbulence that is going to be there,
I could
and
not
that
do
could
Wi-Fi
explain a
now.
lot of the discrepancy.
I would need to
But
get
anyway,
chassis.
Prento Grasshopf number is T-film,
What
based
if
on T-film.
I could put
So Rayleigh number is more than 3 times 10 to the 8,
3 modules.
Yes.
TC.
and it will initially be some turbulent phenomena all the way up till, yep, this is we just highlight it in green
I'm keeping it general.
because it's turbulent. Anything below this, because anything below this, a Rayleigh number below 3 times 10 to the 8, it will not be turbulent anymore. It will be more of a laminar thing. So I think turbulent thing should be
That would be
why, yeah, should be one of the reasons why we are under predicting
Yeah, this could still be
some of the effects, because we are only considering laminar flow. We're only considering laminar flow, so yeah, we may want to have some consideration of that.
compared to
So
compact Rio.
okay, the
Compact
Nusselt
Rio
number of the CFD is then this. I'll just do an equal.
I guess I don't understand.
Yeah, this one's for plotting,
Controllers are.
and this one's based on the correlation.
I guess that's what my.
Okay, it doesn't matter. Can we use the formulas in a bit? Okay, anyway, equals to
What understanding
Did we ever-
the
did we ever-
this one,
we haven't looked at this.
and let's put laminar just to make the difference very obvious to us.
It looks like
Okay,
controllers look just like.
now next thing is the correlation that we want to develop.
It seems like I think it's I guess
Okay.
OS.
So
Like the
two
that
things
has
we
its
need
own
is the
processor.
Rayleigh number, which is this
But I thought that was
S6.
the whole point of the picture.
So Rayleigh number, okay,
Right. Do you mind if I use this?
S6 will not be the Rayleigh number, it will be here, Q6, and the other one will be the parental number at the bottom.
Without an external PC.
The parental number
So
will
don't
be
explicitly say that
here,
for
I6.
compact Rio. Or those let you control a Pixie system from desktops, laptops, or server computers.
You can delete this off.
I see. So I could use
Correlation.
I could use either. This has like higher performance
Does-
modules.
Does a controller controller.
Okay, looks like the discrepancy is even bigger this time, but sure, makes sense. Probably there's some turbulence actually going on. Yeah, I'll just delete this off. Delete this off.
Wait. Go back. I was gonna read. I didn't read it.
So again, we have the same pattern,
Chassis house
regardless how you look
PXI
at it.
modules and controllers, and connect them with a high performance back.
Okay, Nusselt versus
So
CFD laminar
seems like the
and Nusselt correlation
So
versus
if
Rayleigh
you use a PXI, you have to get the chassis.
number. Of course, if you do it versus temperature, I think you more or less get the same trend there.
Mhm.
Okay, but
So I think this is like
now this is with the temperature correction.
Okay.
Okay, so looks like, yeah, we are again under predicting.
Yeah, I
We are
think
under
it's like what it
predicting
is.
the
I think you have the chassis, which is
yeah,
just-
under predicting the heat transfer coefficient and under predicting the Nusselt number.
and
Okay,
I think your
so
chassis,
even
you have to at least put in
after we include temperature variation using film temperature,
like
the
process
same
to happen on your computer
the discrepancy
from
grows
chassis.
for
Depends on
turbulent
if you get a Pixie controller
and remains
or a
for
Pixie
laminar.
remote controller.
correct.
Okay, so
Then
that could be one
also
reason
have
of
to
that,
get the
and of
module
course that could be a mesh
for-
size problem.
for the actual inputs.
So whether
Okay,
I get a Pixie
so
controller or not,
if you take a look at how much difference there is,
whether I decide
it's about 5 times difference. Oh, that's even bigger than the last time.
kind of like
Last time is about 2 to 3 times only.
Yeah.
Now there are 5
Because
times of difference.
it's a decision
So
I'll
that
have
goes to
make
show we
right now,
probably need some
and
fine mesh
nothing else depends on
to make this thing a little more accurate.
it. So we're
Uh,
gonna put C.
let's put coarse mesh here.
So at minimum,
Coarse mesh.
I will leave either a compact
Okay.
Go or a Pixie chassis.
Okay, so
And then three
that
modules.
will be the
Um,
next thing we need to improve
we
on
could still
in
do
the
it
next
as
variation of the simulation.
This is
Yeah. So we have a simulation, but it doesn't quite match up to the results. So we'll need to do some changes. So Nusselt number predicted here is almost 100, you know. So we need a lot more things to predict it correctly. Okay, that's all, folks. I'll see you guys next time. We'll talk about how to improve the accuracy of the simulation. Thanks for watching.